We live in a world where being lost is becoming a memory. With a simple tap on a screen, we know exactly where we are, down to the meter. We take for granted that a blue dot on a map can guide us through unknown cities, track our morning runs, and land airplanes in the fog. But behind this everyday convenience lies one of the most complex and sophisticated engineering achievements in human history. It is a dance of physics, timing, and gravity happening 12,000 miles above our heads. This is the story of the Global Positioning System, GPS. Today we will deconstruct the invisible grid of radio waves, trilateration, and the speed of light that keeps the modern world on track. To understand what GPS is, we must look at its definition and its origins. GPS stands for Global Positioning System. It is a navigation system that relies on a constellation of satellites, ground receivers, and complex algorithms, all operated and maintained by the United States Space Force. While today we use it to find the nearest coffee shop, it wasn't built for us. It was originally designed and built strictly for military use, allowing precise troop movements and missile guidance. It was only in the 1980s that the system was open to the public, transforming from a weapon of war into a utility for worldwide navigation that powers the global economy. The system is vast, but it can be broken down into three distinct operational segments. First, looking up, we have the space segment. This consists of the satellites themselves, orbiting Earth in precise, calculated formations. Second, keeping them in check is the control segment. These are the ground stations scattered across the globe that monitor and manage the health and position of the satellites. And finally, there is the user segment. This is you. It includes the receivers found in phones, cars, watches, and shipping containers. Without any one of these three pillars, the entire system would collapse. Let's journey to the first pillar, the space segment. To cover the entire planet simultaneously, you need a fleet. The GPS constellation consists of at least 24 active satellites at any given time. In practice, there are typically around 30 operational units in orbit to ensure redundancy if one fails. These aren't static, they are moving targets. They inhabit a specific zone known as medium Earth orbit, sitting at an altitude of approximately 12,550 miles above the surface. At this height, they travel at incredible speeds, circling the Earth exactly twice every single day. Why do we need so many satellites? It comes down to visibility. The system is designed so that from any point on the face of the Earth, whether you are in the Sahara Desert or the middle of the Pacific Ocean, at least 4 satellites are visible above the horizon at any time. This number is not arbitrary. As we will learn later, 4 is the magic number required for the mathematics of navigation. While 3 satellites can give you a rough location, the 4th satellite is essential for achieving precise 3-dimensional positioning accuracy, giving us latitude, longitude, and altitude. These satellites are machines, and machines drift. This necessitates the control segment. The brain of the GPS network is the Master Control Station, located at Schriever Space Force Base in Colorado Springs, USA. This master station works in tandem with a network of monitor stations positioned around the world. Their job is vital. They track the satellites' exact paths, ensuring they haven't drifted due to gravitational anomalies. They maintain the correct satellite orbits, and crucially, they update the atomic clocks on board to ensure precise timing accuracy. Without this constant correction, GPS would become useless within days. Now we turn to the user segment. There is a common misconception that your phone talks to the satellites to find your location. It does not. Your device is a passive receiver. It listens. It does not shout. It simply tunes in to the radio signals being broadcast continuously by the satellites overhead. Think of your GPS receiver not as a communicator, but as a super accurate stopwatch. Its primary job is to function as a precision timer, measuring the travel time of signals with extreme precision to determine how far away those satellites are. So, what are the satellites actually saying? The broadcast contains two critical pieces of information. First, it sends ephemeris data. This is essentially a message saying, "Here is my exact position in space." Second, and most importantly, it sends a transmission time. This is an exact timestamp indicating the precise nanosecond the signal left the satellite. These signals travel down to us via radio waves, moving at the speed limit of the universe, the speed of light, which is roughly 186,000 miles per second. This brings us to the core physics of navigation. To find out where you are, your receiver must first figure out how far away it is from the satellite. It uses the simple algebraic formula: distance equals speed multiplied by time. The speed is constant, the speed of light. The time is the difference between when the signal was sent and when your phone received it. For example, if the receiver calculates that the signal took 0.06 seconds to arrive, it multiplies that time by the speed of light to calculate the precise distance. This measurement is called the pseudo-range. Once we have the distance, how do we get a location? Many people confuse GPS with triangulation, which uses angles. But GPS actually uses a geometric method called trilateration. Trilateration relies entirely on measuring distances, not angles. Imagine you are lost in space. If you know you are exactly 12,000 miles from satellite A, you aren't at a single point. You could be anywhere on the surface of a massive sphere with the satellite at the center. To pin you down, we need to intersect spheres. Let's visualize this step by step. We start with one satellite. Your receiver calculates the distance to it. Mathematically, this places you somewhere on the surface of a giant sphere surrounding that satellite. You could be in London, or you could be floating in deep space. A single measurement is not enough to define your location on Earth. We need more data. Now we acquire the signal from a second satellite. We calculate the distance to it and generate a second sphere. When you intersect two spheres, the result is not a point, it is a circle. You are now located somewhere along this ring where the two spheres meet. We have narrowed it down from the whole universe to a single circle of possibilities. But we still don't know exactly where you are. This is where the third satellite comes in. When we intersect a third sphere with that circle, we are left with just two possible points in space where all three spheres meet. One of those points will be on the surface of the Earth, where you actually are. The other point is usually thousands of miles out in space, an impossible location that the computer can easily reject. With 3 satellites, we have technically found your position in terms of latitude and longitude, but the system isn't finished yet. Why do we need a 4th satellite? Well, 3 satellites give us a 2D position. The 4th satellite adds the critical vertical dimension, altitude. It allows for true 3-dimensional positioning, but it serves an even more critical function, timing correction. As we will see, light moves so fast that even a tiny error in your phone's clock can throw your position off by miles. The 4th satellite provides the necessary data to synchronize your receiver's cheap clock with the expensive atomic clocks in space. This leads us to the clock problem. The entire GPS system is based on time. The satellites are equipped with atomic clocks that measure time based on the atomic vibrations of cesium or rubidium atoms. These are incredibly precise, not losing a single second in millions of years. However, your phone uses a cheap quartz clock. It simply isn't accurate enough. Because light travels so fast, a clock error of just 0.001 seconds, a single millisecond, would result in a location error of 180 miles. The fourth satellite helps the receiver mathematically solve for this time error. The precision required is so extreme that GPS satellites must account for the theories of Albert Einstein. Without accounting for relativity, GPS would fail within minutes. First, there is special relativity. Because the satellites are moving at high speeds relative to us, time actually slows down for them. Second, there is general relativity. Because they are far away from Earth's heavy gravity, time speeds up for them. When you combine these conflicting effects, the net result is that satellite clocks run 38 microseconds faster than clocks on Earth every day. If engineers didn't program the system to correct for this, the navigation would drift by kilometers every day. Even with perfect math, the real world gets in the way. We face signal interference. As the radio signals pass through the ionosphere, a layer of the atmosphere filled with charged particles, they are slowed down. This delay tricks the receiver into thinking the satellite is further away than it actually is. On the ground, we face multipath error. In cities, signals bounce off tall buildings like echoes before reaching your phone. This bouncing creates a longer path, making distances appear longer and confusing the receiver. GPS has evolved far beyond just telling us how to get to the grocery store. It has applications beyond maps. In agriculture, precision farming tractors use GPS to plant seeds with centimeter-level accuracy. In banking, the global financial system relies on GPS time to timestamp transactions at ATMs and stock exchanges. In science, it tracks the minute movements of tectonic plates to monitor earthquakes. It even tracks wildlife, revealing the migration patterns of animals across continents. While GPS is the American system, it is not alone. It is part of a larger family of global navigation satellite systems, GNSS. Russia operates GLONASS, Europe has built the Galileo system, and China operates Beidou. Modern smartphones are clever. They don't just listen to GPS. They listen to all of these systems simultaneously. By using satellites from multiple nations, your phone achieves faster fixes and better accuracy than any single system could provide alone. As we look ahead, the future of GPS is becoming even more precise. New generations of satellites are broadcasting stronger signals that are harder to jam, offering improved security and reliability. We are moving towards systems with 3 times more accurate positioning, capable of locating you within 1 to 3 meters. In summary, GPS is a marvel that relies on distance, speed, and time, using trilateration with at least 4 satellites. It requires atomic clocks and relativity corrections to function. It is a free utility, invisible but essential, powering the modern world.